So this lesson is going to take some formulas that you know and explain where they come from, how they work, and it's going to take some develop some formulas that you may not be familiar with as well at the very end. So we'll kind of build toward that. So first off, the rectangle, unit squares, tiling a rectangle, very simple, length times width, base times height. We're not going to go into that too much. Parallelogram, the way you can see it is to draw a perpendicular within the parallelogram, take that triangle and slide it over. And when you do so, you end up with a rectangle that's base times height, the same as the parallelogram was. So that's where that formula comes from as well. With a triangle, there's a couple of ways it can be visualized. We can rotate a triangle around the center of its hypotenuse if it's a right triangle. That's going to form two congruent triangles that make up a rectangle. So 1/2, if I rotate, I create a second triangle. Those two would be the area of the rectangle, so half of that area is one of the single triangles. If you had an obtuse triangle, a non-right triangle, you can split it into a right triangle, creating triangles A and B, and then do the same procedure with both of those and rotate them both to make rectangles. So triangle A is half of rectangle A, and triangle B is half of rectangle B, and so it's half of the areas combined. We know additionally that we also have our trig formula and our semi-perimeter formula, so those are in addition to the 1/2 base times height. And finally, to visualize an obtuse triangle, this one's a little trickier. What you can do is you don't want to surround it with a rectangle because then you won't be involving the base, you'll be extending past the base. So what you can do is draw the rectangle so that it does touch the base itself. Bring that rectangle up to the height of the original triangle. And then if you were to connect that back to the corners of the rectangle you have formed, because the base and the height are the same as the obtuse triangle, you end up with a triangle that's half of the rectangle that it needs to be. So that's why it works for an obtuse triangle too. All right, so having done all that, we'll get to some slightly more complicated ones. If we're talking about a trapezoid, there's a couple ways to do this. First way to do it is to break it up into a rectangle and two triangles. So the first triangle is called A, second one's C, third one's B. The rectangle is C, the triangles are A and B. So what we have here is a base 1 and a base 2. Those are the parallel sides. And if we just call the triangles X and Y, then what we can say is that the base 2 minus base 1, right? If I had base 2 and I take out base 1, what I have is this X plus Y, and that's going to come up in a second. So we're splitting the base 2 into three separate sections, the rectangle base and the two triangle bases. All of them have the same height. All right, so the area of the trapezoid would be equal to the area of all three sections. The area of the first triangle would be 1/2 x times h, because the base is x and the height is h. The area of the rectangle is just going to be base 1 times height. That's obvious, length times width. And then the third triangle is 1/2 y times h for the same reason as the first one. So what we do then is a little bit of algebra. We take the first term and the second and the third term and combine them, and at the same time factor out a 1/2 and an h. So if I do that, I'm left with x plus y. So I'm taking the first term and the third term and factoring out a 1/2 h. Then because I have that sum that I was talking about before, that x plus y, we can say that the x plus y part is equivalent to b2 minus b1. That's going back to the diagram. X plus y is the same as the whole b2 minus b1. X plus y is what's left over, so we can just replace that. All right, continuing on with the algebra then. If I distribute the 1/2 h to the b2 and the 1/2 h to the b1, I get this equation here. And if I then just do like terms, this b1h and this 1/2 b1h can be subtracted. And that gives me plus 1/2 b1h. And then finally, take out the half, take out the h, and we have the formula for a trapezoid. So, formula for a trapezoid can be derived using three area formulas and some algebra. The other way to look at it is to do a rotation, to take a trapezoid, find the midpoint of one of the sides, and rotate it so that you end up with a trapezoid that's upside down where we've duplicated it, we've preserved all the distances, we've preserved all the areas, and created a parallelogram with the same B1 plus B2 on both parts. So the area of the parallelogram would be equal to base times height, but we could write it as B1 plus B2 times height. Right, that's the base of the parallelogram, and that's the height. So then if I want the trapezoid, it's just half of that because I doubled it to get the parallelogram. So that's another way to look at it. All right, and finally, regular polygons. So regular polygons have all sides congruent, all angles congruent. They have a center, they have a radius. That radius is coinciding with the circumscribed circle, and there's several images of that here. So if you connect a center to a vertex that touches the circle that goes around it, that's a radius. If you create a perpendicular from the center to any side, that's called an apothem. So that apothem is all these perpendicular segments from the center point. Radius goes to a vertex, apothem goes perpendicular to a side. All right, so with that vocabulary established, the more popular regular polygons that you see here, formula for an interior angle, we've been through this before, it's the sum of all the degrees divided by n. So each of these interior regular polygons areas can be found by adding together all of the triangles that these central angles make. The number of triangles that the central angles can make is equal to the number of sides in the polygon, because you can draw a triangle to any of these sides. So an octagon is going to have 8 triangles, a hexagon will have 6, and so on. So to get the area of the polygon, what we want to do is find the area of one of the triangles and multiply it by the number of triangles, which would just be n. So if I do the formula for area of a triangle, 1/2 base times height times n, the side of the triangle is the base, the apothem is the height. So if I am trying to, and this is going to be n, so if I want to find the area of the triangle, those can be rearranged. And the reason I would rearrange them is because n times the side length, n times b, this combines to give me the perimeter. Right? The perimeter of the figure is just the number of sides times each side length. So to simplify this formula as far as it'll go, it's 1/2 times the apothem times the perimeter. So that's a really nice formula to know, 1/2 a times p. To use this formula, what we need to know is this apothem, which is perpendicular, and the perimeter, meaning one side, and times the number of sides. Usually we have enough information to get those or to use them in a diagram. One other version of the area of a polygon formula that we can use, and this is if we know the radius. So the apothem is the perpendicular. Remember, I'm just going to use this diagram of the octagon up here. This is the apothem here. If we don't know the apothem and we know the radius, we can use trig to calculate the apothem. But we also have a way to just use the apothem the radius, because remember, we can always do 1/2 xy sine theta. All right, so this next formula is going to work off of that. If the triangle is 1/2 xy sine theta, in these regular polygons, x and y are both the radius of the polygon. So that can be converted to r squared. And the angle is just the central angle. So to do the polygon, we can put an n in there as well, because remember, there are n triangles within the polygon. So basically what this formula does is it uses our non-right triangle area formula, substitutes a radius and a number of side lengths, and this then becomes a very easy formula to use if we know the radius. We use this formula if we know the apothem, we use this formula if we know the radius.